Now, let us look into the problems that as corresponding to the theory that we discussed so far. Let us consider a discrete time signal x of n whose DFT is given as x1 of k and the FFT of the same is given as x2 of k. It's given that x1 of k is equal to x2 of k for every k. We need to see if the statement is correct or not. We know that FFT is just a alternate implementation of DFT for faster realization of DFT. So from this we can say that x1 of k should be equal to x2 of k for every k. Now let us consider another problem as a part of which it is given that there is a signal x of n whose autocorrelation function is given as Rx of n and autocovariance function is given as Cx of n. There are three statements given. We need to find if the statements are true or not. The statement 1 says that Rx of n is equal to Cx of n for every n. The statement 2 is that Rx of 0 is equal to variance of x. The statement 3 is that abs of Rx of n is less than or equal to abs of Rx of 0. We know that from the definition of the autocorrelation function, Rx of n should be equal to expectation of xn multiplied by x, where xn is the shifted version of x. Also, the autocovariance function Cx of n can be given as expectation of xn minus mx multiplied by x minus mx, where mx is the mean of the signal x. From this, we see that the autocorrelation function Rx of n is not equal to autocovariance function Cx of n for every n, and the equality holds good if and only if mx is equal to 0. From this, we can say that the statement 1 is not correct. Similarly, we can show that Cx of 0 is equal to expectation of x minus mx whole square, because when n is equal to 0, xn would be equal to x. From this we see that Cx of 0 is equal to variance of x and Rx of 0 is equal to variance of x if mx is equal to 0. From this we can say that the statement 2 is also not correct and it holds good if and only if mx is equal to 0. Also from the property of the autocorrelation function, it is that the abs of Rx of n is less than or equal to abs of Rx of 0. So from this we can say that the statement 3 is correct. So here we use the definition of autocorrelation function and autocovariance function along with their properties to point out the statements that are correct. Now let us consider another problem as per which it is given that the DFT of a signal x of n is given as x of k, which is equal to 1 comma 2 comma 3 comma 0. that is the length of the signal is n is equal to 4. We need to find the value of the dtft of the signal x of n, that is x of e power j omega at omega equal to pi. We know that x of e power j omega at omega equal to pi is equal to x of k, where omega equal to 2 pi k divided by n. Upon substituting n is equal to 4, we see that omega is equal to pi by 2 k. But it is given that omega is pi. From this we see that k is equal to 2. Therefore, the value of x of e power j omega at omega equal to pi is equal to x of 2. From the given DFT, we see that x of 2 is equal to 3. So, the value of x of e power j omega at omega equal to pi is equal to 3. Now, let us consider another problem, as per which it is given that there is a continuous time signal y of t, which is given as x square of t, whose Nyquist sampling frequency is given as 12 kHz. Please note that y of t corresponds to a class of signals whose Nyquist sampling frequency is 12 kHz. Now we need to find the bandwidth of the signal x of t from above data. From the given data that y of t is a class of continuous time signals whose Nyquist sampling frequency is 12 kHz, we need to find the bandwidth of x of t. From the given data, we see that Nyquist sampling frequency of y of t is 12 kHz. That implies the bandwidth of y of t is 6 kHz. As it is given that y of t is equal to x square of t, which can be written as x of t multiplied by x of t. By taking Fourier transform on both sides, we see that y of j omega, that is continuous time Fourier transform of y of t, is equal to x of j omega convolved with x of j omega multiplied by k. That is, the multiplication in time domain is equal to convolution in frequency domain. As y of j omega has a bandwidth of 12 kHz, we can say that the bandwidth of x of j omega can be something like 6 kHz. Sorry, as y of j omega has a bandwidth of 6 kHz, we can say that the bandwidth of x of j omega is 3 kHz. So from this we see that the bandwidth of x of t is equal to 3 kHz. Now let us look into another problem, as per which it is given that there is a signal x of n which is written as sine of omega cn divided by pi n whole square convolved with sine of pi by 4 n divided by pi n. This is equal to sine of omega cn divided by pi n whole square. We need to find the maximum value of omega c possible from this. We know that sine of omega c n divided by pi n will have a dtft of 1 for mod omega less than or equal to omega c, 0 for omega c less than or equal to mod omega less than or equal to pi. That is, sin omega c n divided by pi n is a low pass filter with cutoff frequency of omega c. From this, we can also say that sine of omega cn divided by pi n whole square is product of two LPF filters in time domain. So it's equal to convolution in DTFT domain. So this will have a cutoff frequency of 2 omega c. From this, we can say that x of n should be equal, x of n is actually a signal of bandwidth to omega c. Now the same is convolved with an LPF with a cutoff frequency of pi by 4, which is as shown, that is sine pi by 4 divided by pi n. To get x of n back after convolution, we can say that the 2 omega c should be less than or equal to pi by 4. Otherwise, due to low pass filtering, x of n gets altered and we may not get the original x of n back. So from this we can say that 2 omega c should be less than or equal to pi by 4. That implies omega c should be less than or equal to pi by 8. From this we see that the maximum value of omega c possible is pi by 8 as per the given condition. Now let us consider another problem as per which it is given that there is a signal x of n whose length is n is equal to 10. It is given that the DTFT of the signal of x of n is given as e power minus j omega and DFT of x of n is given as x of k. We need to find x of 5 from this given data. We know that x of k is equal to x of e power j omega, where omega equal to 2 pi k divided by n. From this, we can write that x of 5 is equal to x of e power j omega, where omega is equal to 2 pi into 5 divided by 10, that is equal to pi. So upon substitution, we get the value as e power minus j pi, which is equal to minus 1. From this, we see that the value of the DFT of the given signal at k equal to 5 is minus 1. Now, let us consider another problem as per which there is a discrete time LTI system whose phase response is given as phi of omega is equal to 3 omega plus tan inverse omega radians per second. We need to find the group delay of the LTI system at omega equal to 1 radian per second. We know that the group delay g of omega is given as minus d phi by d omega, which can be written as minus of 3 plus 1 by 1 plus omega square, because the derivative of 3 omega is 3 and the derivative of tan inverse omega is 1 by 1 plus omega square. From this, we can see that group delay at 1 radian per second is minus of 3 plus 1 by 2, that is equal to minus 3.5. From this, we can say that the group delay of given LTI system at omega equal to 1 radian per second is minus 3.5. Now, let us consider another problem as per which there is a LTI system which has zeros at A and 1 by A star, and it has poles at B and 1 by B star. We need to find the category to which the transfer function of the system belongs to. That is, if it is linear phase or minimum phase or magnitude transfer function or all pass. We know from the given data we see that zeros form conjugate reciprocal pairs and poles form conjugate reciprocal pairs. From this we see that, based on this information, we need to find the category to which the transfer function belongs to. In case of linear phase system, zeros form conjugate reciprocal pairs and there is no and it is expected that there will not be present any poles. So the given transfer function or the system is not linear phase. In case of minimum phase system, if it is causal, poles and zeros are inside unit circle. So this is also not the given category. In case of alpha system, poles and zeros together form conjugate reciprocal pairs. So alpha system is also not belonging to the same category. In case of magnitude transfer function, zeros form conjugate reciprocal pairs and poles form conjugate reciprocal pairs individually. From this, we can say that the given transfer function belongs to the category of magnitude transfer function. So C is the correct option. Now let us consider another problem as per which there is a filter structure given which is as shown. It takes an input of x of n and there are weights that are marked as zero point 0 t and zero point 3. There are delay elements as shown which are actually Z inverse and the outputs of the branches are added to get an output of y of n. We need to find the LCCDE that represents the LTI system. From the given plot, we see that the output y of n can be obtained by marking the signals at different points. The signal at the point that we marked is x of n, and the signal at the end of zero point 0.02 branch is zero point 0.02 x of n, and the signal at the end of the zero point 3 branch is zero point 0.006 x of n. From this, we can say that y of n is equal to x of n, that is occurring at the end of this branch, plus the signal at the end of this branch, which is zero point 0.02 x of n minus 1, and the signal occurring at the end of this branch, that is zero point 0.006 x of n minus 1. From this, we can write the LCCDE as y of n is equal to x of n plus 0.026 x of n minus 1. From this, we see that the given filter structure can be represented as an LCCDE, which is y of n is equal to x of n plus 0.026 x of n minus 1. Now, let us consider another problem as per which there is a filter structure given as shown in the figure. It contains the delay elements as marked, and also please note that the weights of different branches, if not mentioned, should be taken as 1. Now, from this plot, from the diagram given, we need to find the impulse response of the LTI system whose block diagram is given here. We see that from the given block diagram, y of n can be written as 2 multiplied by x of n plus x of n minus 4 plus 3 multiplied by x of n minus 1 plus x of n minus 3 plus x of n minus 2. This is of the form of sigma k equal to 0 to infinity h of k multiplied by x of n minus k. From this, we can write the impulse response h of n as 2 comma 3 comma 1 comma 3 comma 2, where the value of 2 corresponds to the instant n is equal to 0. So from the given filter structure, we can realize the impulse response as h of n is equal to 2 comma 3 comma 1 comma 3 comma